In this video, we're going to work example problems that involve finding roots of complex numbers. So for each of the following, we're going to be given a complex number. We want to find all cube roots of that complex number. And we also want to graph each cube root as a vector in the complex plane. So we're only going to be finding cube roots here, but it's the principles are exactly the same for any root, any nth root. But in the next video, we're going to solve some equations, and then with those, we'll practice finding other roots other than cube roots. So, okay. First of all, I want to point out that they're mentioning nothing about principal cube roots or principal roots. Okay, so I've talked about this before. You know, we're not thinking about radicals in any way here. But even if we were finding the principal root of the principal cube root of this complex number z, we're still not going to be thinking about radicals anyway. So like for each of these problems, I'll go ahead and point out what the principal cube root is in addition to all of the other roots. We'll point that out. But even then, we're still not thinking about radicals. Okay, all they're asking us is that there's two ways you look at roots. You think about the principal nth root, which if you're just thinking about real numbers, then you think about radicals. But if you think about complex numbers, we haven't talked about the symbology for that yet, but we'll talk about that in the complex analysis course. But with a principal nth root, it's going to be one root, one number. That's one way you can talk about roots. The other way is when you just say, not principal, you just talk about what are all of the nth roots of this number. So in that case, you're asking, in general, what are all of the numbers when you take them to the n power that you get the number in question? And that's what we're doing here. We're trying, for each of these, we're answering the question, what are all of the complex numbers that when you take them to the third power, you're going to get this? That's the question we're asking, we're answering it for each of these problems. So, okay, so here's this complex number. Let's put it in rectangular form. So cosine of 0 is 1. Sine of 0 is 0. So this is just the number 1. But I guess if you want to be more specific, it's 1 plus 0i as a complex number, but we'll just leave it as 1. Okay. Now, we're going to have, we know that for any complex number, no matter what it is, you know, this is a complex number, there's going to be exactly n nth roots. So that means we're going to have exactly 3 cube roots here. And then, but all their radiuses are going to be the same, and the radiuses are going to be given by, you take the principal cube root, the principal nth root of the radius, so you have it in polar form. You want to put it in polar form, the complex number you're working with, put it in polar form, and then first look at what the radius is and take the principal nth root of that radius. That's 1. So each of these are going to have radius 1. And so obviously then the difference is going to come in with what the angle is. So the angles are alpha. You take the angle of the number you're trying to find the root of in polar form. You put that and then plus 360 or 2 pi times some positive or negative integer k, and then you're dividing by 3. You divide by n. That's in general you divide by n. And then the 3 values are going to correspond to k is equal to 0, 1, and 2. There's going to be 3. You put 3 k values or n k values, starting at 0 and counting up an integer from there. So in general, you'd go all the way to n minus 1. So like you can see, we stopped at 2 here. We stopped at n minus 1 here. Okay, there we go. So alpha 1 is going to be, so k is equal to 0. It's going to be 0 degrees. Alpha 2 is going to be, k is equal to 1. So that's 360 divided by 3. So that's 120. Okay, alpha 3 is, so 360 times 2 is 720, and then 720 divided by 3 is 260. Or no, is that right? No, it's 3 times 4. Yeah, 3 times 4. So this is 12, and 3 times 4 is 12, so it's 240. Okay. And so there we go. So we can, remove the 1 because it's just, you don't have to have the 1 there, right? So what we're left with is we're going to have cosine of 0 plus I sine of 0. Then we're going to have cosine 120 plus I sine of 120. And then cosine of 240 plus I sine of 240. Okay, now this first one is just 1 itself, which makes sense because we know one of the cube roots of 1 is 1 itself, right? In fact, the principal cube root of 1 is 1. Okay, now what's interesting though is that the principal nth root of any complex number is just going to be the number corresponding to k is equal to 0, which, so the principal cube root in relation of 1 in relation to a radical is 1, and in just relation to the, evaluating the cube roots as a complex number, it's also 1. So it kind of makes you think, well, that's great then. We could have just put this into a radical, but it unfortunately, it doesn't always work out that way. So for example, if we have the principal cube root of minus 8 as in a radical here, well, we know that's minus 2. But when you do this whole process with minus 8 plus 0i, it's actually the second root. The k is equal to 1 root comes out to be minus 2 plus 0i, and the first one is like 1 plus I root 3. And that's, by the complex analysis, that first one is the principal cube root. So that's the issue where we just don't want to mix radicals with. We'll clear all that up in the complex analysis course, but we just don't want to be mixing radicals with complex numbers. It's just for the moment. Okay, so all right, now let's put this in rectangular form. So we've got cosine 120 sine 120. So minus 1/2 plus root 3 over 2i. Okay, minus 1/2 plus root 3 over 2i. Now let's see. Cosine of 240 sine 240 minus 1/2 minus root 3 over 2i. And there we go. So these three numbers here, if you cubed them, and we know how to cube, we know how to take powers of complex numbers. That's what we were doing in the previous example problem video. So if you cubed any one of these, you're gonna end up with 1 or 1 plus 0i, and that's the 3 cube roots. And this is the principal cube root, which actually happens to agree with what the radical would say is the principal cube root. Okay, now let's go ahead and graph these. And they want us to, the reason why they're wanting us to graph them in the complex plane is because it's illustrative of some symmetry that's involved with roots of complex numbers. So the first form of symmetry is that with any nth root, they're all going to have the same radius, right? So what that means is that they're all going to be contained on a circle in the complex plane. In this case, it's going to be a circle of radius 1. Okay, and then, but another reason is because, okay, let's plot these. You've got, there's x1, and then the next one's going to be at 120 degrees. So that's about, what, 30 degrees past the vertical. Next one's at 240. That's 30 degrees in front of the negative vertical. Okay. So there is x1, x2, 2, and x3. So the other form of like symmetry here is the fact that for any nth root, the roots are going to be equally spaced, like all the way around. So you start at the first root, the vector corresponding to the first root, and then the angle between the first vector and the second vector is going to be the same as the angle between the second vector and the third vector, and the same as the angle between the third vector and the first vector every time. You can kind of see that here, and so that can help us to it can make it easier to get these angles. We don't have to keep plugging in k values, because all you have to do is, if you think about it, it's since they're equally spaced, there's two things here. Since they're equally spaced every time, no matter what, and they're equally spaced all the way around the circle, so 360 degrees is there. That's what they're equally spaced around. Okay, but then also for any nth root, you're going to have n roots. So, like in other words, here we know we're going to have these three roots equally spaced around 360 degrees. So we can, before we even start the problem, we know that if we're taking a third root, we know that the roots are going to be spaced. It was 120 degrees. We already know that going into it. And but if we were doing the fourth root, we know they're going to be spaced 90 degrees apart, all four of the roots. So all we needed to do was we could have just gotten this first angle here, the angle corresponding to k is equal to 0, and then we knew from there the next one was going to be 120 and the next one was going to be 240, because they're going to be spaced 120 degrees apart. Okay, so let's see, 8, we want to find all the cube roots of 8 cis 60, which we know is 8 cosine 60 plus I sine of 60. Okay, now let's put this in rectangular form. So we've got, if we draw the 30, 60, 90 reference triangle, 30, 60, so okay, 1, root 3, 2. And yeah, and just FYI, we don't have to put this in rectangular form. We do roots and powers. We need polar form. I'm just doing this because I think it's illustrative to see you starting at the rectangular form and ending at the rectangular form. But technically, we didn't have to do this. We don't have to do this. So, okay, cosine 60 is 1/2. So 8. Okay, sine 60 is root 3 over 2. So you multiply that, you're going to get 4 plus 4i root 3. So 4 plus 4i root 3. And I like converting it to rectangular form first, because, or at least showing the rectangular form first and the rectangular form at the end, because I feel like the polar form is just like a tool that you use, because most commonly you're going to work with in rectangular form, right? For like complex numbers, that's the most common. But you convert to polar to do like powers or roots or some sort of calculation. Then you convert it back. To me, that would be the most common application. So I like showing the before and after of rectangular. All right. So now we're going to have these three roots. Okay, x2. And they're going to have the same radius given by the principal cube root of this r value here. So what is the principal cube root of 8? That's 2. So they're all going to have radius 2. That's why they're all going to be on a circle in the complex plane of the same radius, in this case 2. So, okay. Now the angles are going to be, so alpha is equal to, you put the angle of the root, 60 degrees in this case, plus 360 or 2 pi if you're in radians, times k, all over, in this case it's 3, but in general it would be n. All right, but now k is going to be equal to, we're going to have 3 values, so 0, 1, and 2. So with k, with k is equal to 0, we're going to get alpha 1, and that's going to be 60 divided by 3, it's 20. Okay, so the first root is 2, then cosine 20 plus I sine of 20. Okay, and that's the principal cube root of this complex number here. Okay, so now alpha 2, we could just plug k is equal to 1 in again, but we know they're going to be spaced 120 degrees apart, so this is going to be 140. Alpha 3, we could plug k is equal to 2 in, but it's easier just to see that this is going to be 260. So we've got cosine 140 plus I sine of 140, and then cosine of 260 plus I sine of 260. Okay, now I want to convert these to rectangular, but you don't have to do that. So, okay, cosine 20, and then times 2, and then sine of 20 times 2, 1.88 plus 0.68i. Okay, now let's see. Cosine 140 times 2, and then sine of 140 minus 1.53 plus 1.29i. Okay, now let's see. Cosine of 260, and then sine of 260 minus 0.35 minus 1.97i. And there you go. There are if you cubed any of these numbers, you're going to get this. Okay, now let's plot them in the complex plane. So they're going to have this common radius of 2. Okay, then let's see. The first one's going to be at 20 degrees, so right in there. The next one's going to be at 140. So 135 is about 45, so like right in there. And the next one at 260, that's right before the negative vertical 270. And you can see they're evenly spaced, right? They're all 120 degrees apart. And we could put, I guess we could put this 20 degrees. Yeah, so x1, x2, x3. Now, again, this is the principal, according to like complex analysis, this is the principal cube root of this. But that doesn't mean we're not going to do this. It's tempting to think about it like, okay, the principal cube root of 4 plus 4i root 3 is 1.88 plus 0.68i. But no, we don't want to do this. We're going to talk about this later. Until you've taken complex analysis, I haven't posted that playlist yet, you don't want to do this. All you could do is just go off to the side and make a statement that the principal cube root of 4 plus 4i root 3 is 1.88 plus 0.68i. Don't put any radicals. Because it's like if you put it in a radical, then it's like saying that, okay, so we know that the principal cube root of minus 8 is minus 2, but we also know in complex analysis that if the principal cube root of minus 8 is 1 plus I root 3. So, well, which one is right? That's what we'll talk about later. Okay, so we want to find the 3 cube roots of minus 8i. Now, in polar form, this is going to be, so 8, then, and so minus 8i, that's going to have angle 270, right? That's the negative vertical, plus I sine of 270. Okay, So now we've got, let's see, we're going to have 3 roots, and they're all going to have radius, the principal cube root of 8. So 2, 2, 2. Okay, now the alphas are going to be just put that 270 and then plus 360 times k all over 3. And then with k is going to be 0, 1, and 2. So now the alpha 1 is going to be, so k is equal to 0. You're left with 270 divided by 3, that's 90. Okay, now they're all going to be spaced 120 degrees apart. So let's see, it would be next one would be 210, and then the next one would be 330. So we've got 2 cosine 90 plus I sine 90, 2 cosine 210 plus I sine 210, and then 2 cosine 330 plus I sine 330. Okay, so there's the 3 roots. Let's put them in rectangular form. So, okay, cosine 90 is going to be 0. Sine 90 is going to be 1, so this is 2i. All right. Let's see. Cosine of 210. Okay, sine of 210. So, okay, multiplying by 2, you got minus root 3 minus I. So, minus root 3 minus I. Okay, now cosine 330, sine of 330. So okay, multiplying by 2, root 3 minus I. And there you go. So you cube any of these, you're going to get minus 8i. So I mean, we can look, let's cube 2i. So 2 cubed is 8, and then we've got I cubed. Now we know I cubed is I squared times I, so this is minus 8i. There we go. All right, now if we plot these in the complex plane, you've got real, imaginary. In the complex plane, we've got, let's see, they've all got the same radius to k. Now we've got, let's see, we start at 90, and then 210 would be 30-degree reference angle, like around there, and then 330 would be 30-degree reference angle here. And there we go. So we start off at 90. We've got x1, x2, x3. Okay, minus 64. What are all of the cube roots of minus 64? And you know, this is interesting because it's like the principal cube root of minus 64 is, you know, in terms of a radical, is minus 4. And actually, but even in general, if you're just thinking about real numbers, what are all the numbers that when you cube them, you get minus 64? There's only one, minus 4. So now let's see what happens when we, let's see what in terms of the complex analysis, which you can think about is actually the more reality of the situation. What is going to be the first cube root of minus 64? So, okay, this is in polar form. We've got, it's cosine of 180. The angle is 180 plus I sine of 180. Okay, so let's see. We've got x1, x2, x3. Okay, these are all going to have the same radius, which is going to be the principal cube root of 64, so that's 4. So 4, 4, 4, and then, okay, now the angles, same procedure each time. You just write the angle of the root, and then plus 360 or 2 pi times any integer, positive or negative integer k over the nth root, so that's 3 in this case, but k is going to be limited to be 0, 1, or 2. Okay, so alpha 1 is k is equal to 0. You have 180 divided by 3, that's 60. Okay, and then the rest are going to be 120 degrees away from, they're all 120 degrees apart. So we've got 180, and then we've got, let's see, what would that be? 300. Okay, so cosine 60 plus I sine 60, cosine 180 plus I sine 180, and then cosine 300 plus I sine 300. And you see the issue. You see the issue, right? Let's put these in rectangular form. So cosine 180 is negative 1, sine 180 is 0. There's negative 4. Well, that's not the that's the second. The negative 4 here, the fact that we had the principal cube root of minus 64 was negative 4. Well, yeah, there's one of them. That's one of the roots for sure, but it's not the principal root. So that's the issue. According to complex analysis, this should be, so let's see. We've got, the 30, 60, 90 reference triangle, we've got 1 root 3, 2. So cosine 60 is 1/2. 1/2 times 4 is 2. Sine 60 is root 3 over 2. So plus 2I root 3. Is that right? Root 3 over 2 times 4. Yeah. So according to complex analysis, this should be, so that's the confusion. But again, just don't worry about it. We'll talk about this in the complex analysis course, and we'll settle a lot of this confusion. All right. Now 300 has reference angle 60 degrees in the fourth quadrant. So that would be like, we're going to have in the fourth quadrant, we're over here. So we've got, it's 60-degree reference angle, 2 minus root 3, and then 1. So cosine of 300 is 1/2. So we'll have a 2 here. And then sine of 300 is minus root 3 over 2. So that's going to be like that. And there you go. There's the 3 roots. If you cube any of these, you're going to get minus 64. If we plot these in the complex plane, they're all going to be on a circle of radius 4. Okay, we start off at 60. And then 180. And then 300. Okay. So we've got x1, x2, x3. Okay, 1 plus I root 3. We want to start by converting this to polar. So the radius is going to be, so root 3 squared is 3, 1 squared is 1. 3 plus 1 is 4. Principal root of 4 is 2. Okay. Now the angle is going to be, so we've got, if we think about arc tangent of root 3 over 1. Okay, so the 30, 60, 90 triangle. 1, root 3, 2. So tangent of 60 is root 3 over 1. Okay, now what quadrant are we in? We're in the first quadrant, so the angle is 60. Okay, so there we go. We're in polar form now. Now we can do the roots. So they're all going to have radius, the principal cube root of 2, like with the radical. So we're thinking about real numbers. That's the radius of each one of these. Okay, so now what are the angles going to be? Okay, what we do, so alpha is going to be, we put 60 degrees plus 360 times k all over 3, with k is going to be 0, 1, or 2. So alpha 1 is 60 divided by 3 is 20. Alpha 2, we add 120. Alpha 3, we add another 120. That's it. So cosine 20 plus I sine 20, cosine of 140 plus I sine 140, cosine of 260 plus I sine of 260. Okay. So we could put these in rectangular form. So 2 to the 1/3, okay, times cosine of 20, and then, come on, and let me do, okay, and then this times sine of 20. Okay, 1.18 plus 0.43i. Okay, let's see. Now we've got cosine, and we want to do 140. Okay, now all right, minus 0.97 plus 0.81i. Okay, now with 260, we've got cosine 260, and then minus 0.22 minus 1.24i. And there we go. You cube any one of these, you're going to get this. Now, and this is the principal root. So now, okay, let's plot these in the complex plane. So they're all going to be on the same circle of radius, the principal cube root of 2. Okay. First one is going to be at 20. Second one at 140. Third one at 260. Okay, so we're at about 20 there, or at 20, not about 20. And there we go. Okay, what are all the cube roots of this complex number? Let's convert it to polar. So 2 root 3 squared is going to be 4 times 3. So what's the radius here? 4 times 3 is 12 plus 4. Okay. So 4. All right. Now, cosine of, we've got, so the inverse tangent of, this is 2 over minus 2 root 3. So that's 1 or minus 1 over root 3. Okay, so looks like we can use the 30, 60, 90 triangle again. So 30, 60, 1, root 3, 2. So, okay, inverse tangent minus 1 over root 3 is, tangent of 30 is 1 over root 3. So, but it's negative. We're in the second quadrant. So this would be what? Minus 30, right? That's what would actually come out of the inverse tangent function in this case would be minus 30. Yeah. So, but, okay, but we need to get an angle. That just gives us some information here, but we really need to look at, so this angle or this complex number here is in what quadrant? So negative in the x, positive in the y, so it's in the second quadrant. So we're really just looking for what angle in the second quadrant is going to have reference angle 30 degrees. That's what we're looking for because the tangent is going to be negative in the second quadrant. So that would be what? That's 180 minus 30, 150. So that's the angle. That's the, it's kind of confusing putting the theta like this, but, it's technically the angle is going to be 150. But again, I don't want to make it seem like the arc tangent of minus 1 over root 3 is 150. But yeah, this is going to be 150 plus I sine, and there we go. Now it's in polar form. Okay, so now we have 3 cube roots. Each of them are going to have the same radius given by the principal cube root of 4. Okay. Now the angles are going to be, we do 150 plus 360 times k divided by 3 with k being equal to 0, 1, and 2. So with k equal to 0, that's going to be alpha 1. We've got what? 150 divided by 3 is, okay. 3 times 5, yeah, it's 50 degrees. So alpha 1 is 50 degrees, and then they're going to be spaced 120 degrees apart. So the next one is going to be 170, and alpha 3 is going to be 290. So we've got cosine of 50 plus I sine of 50. We've got cosine of 170 plus I sine of 170. And we've got cosine of 290 plus I sine of 290. Okay. So now we can put this in rectangular form. So we'll start with, let's see, 4 to the 1/3, okay, times, all right, cosine 50, and then 4 to the 1/3 times sine 50. So 1.02 plus 1.22, or no, 1.02 plus I, or 1.22 I. Yeah. There we go. Okay. Next, we want to do cosine of 170 minus 1.56 plus 0.28i. Okay. Let's see. Now, $290.54 minus 1.50i. And there we go. You cube any one of these numbers, you're going to get this. And this is the principal third root of this. So, okay, now let's graph these in the complex plane. Okay, they're all going to have the same radius of principal third root of 4. Okay, so we've got, let's see, we start at 50, about there, then 170, right there, then 290, about right there. Okay, x1, and there we go.